I am going to go through this outline. Introduction, objectives, current research in the area, results and discussions, typical commercial plans, conclusions. The current situation, millions of tons of waste electrical equipment generated every year. If I look at the work done by Q and Forsberg in 2003, Ogun second, HR 2009, Yang HR 2017, Zhang in June 2016. This is a new waste stream, or maybe it's quite in existence for quite a while, which is currently gaining a lot of prominence because of the sheer volumes of the waste that is generated, along with its environmental impact. Now, when you go to our area where we have what is known as secondary metallurgy, then we can view waste electrical equipment as a raw material. And when we begin to do the utilization of this secondary raw material for the production of metal values, we call the process urban mining. Now, waste electrical and electronic equipment, they are very important. So they are a very valuable raw material because they contain the precious metals groups, gold, silver, and then the platinum group of metals. Platinum is palladium, and so on and so forth. Now, why must we worry about waste electrical and electronic equipment? Now, we must worry because, one, of the sheer volume. The volume that is generated is monumental. As you can see in the slide, various forms of weed are generated every year. Now, this includes all mobile phones. Another reason why we must worry about waste electronic and electrical equipment is the environmental impact. People must eat a living, and in doing so, they will do everything possible to create a living. And because WEE consists of heterogeneous materials, after dismantling, they need to get the metals out, which they do by incineration. And this form of incineration is a good form of incineration. And because we contains a lot of heterogeneous materials, burning this in the open usually results in the production of carcinogenic materials into the environment. We are all, aware of Ghana being labeled, especially areas around the Aviation Fuel, as the most polluted areas, I think, in West Africa, if not the whole of Africa. So we must be worried about waste electrical and electronic equipment. Certainly, we need some innovative measures to be able to manage this category of waste stream in order to generate jobs and also not to do a lot of damage to the environment. Now, let's look at the current state of waste electronic equipment in Ghana. Move around Abubushi, Jamestown, and Co. Well, people are selling their old TVs. Certainly, mom must survive. And currently, if you look at the present job situation in the country, the only way that we can prevent the young men from resorting to crime is probably for them to look at ways and means of generating employment by themselves. So they certainly must survive. Now, look at the slide. And you see that various forms of WEEE have been dismantled. These are guys who are looking for metals, various forms of metals and materials so that they can sell and then make a living. Now, the end results. So after dismantling this electrical equipment, what happens? How do we discard the unwanted materials? Do we call this waste or a resource? The next slides will show us whether these are materials meant for the landfill site or something can be done about this to create jobs. Now, one difficult thing about WEEE, as I said earlier, is the heterogeneity of the material. In fact, it comes along with so many materials put together, polymers, with plastics, metals, different forms of metals, refractory oxides like concrete, and so on and so forth. How then are we able to separate the metals that we need without causing harm to the environment? It is a heterogeneous material, and like all heterogeneous materials, it is very difficult to handle them. Like I was saying, metals, glass, plastics, wood, paper, refractory oxides, they are all there. But our focus is to get the metals out. And if you see, look at what is happening in several suburbs of Accra, where people will burn this in the open. Their ultimate goal is to get the metals. Whatever happens, the rest of the waste, they don't care. It's not their duty. Are we safe? Africa has been, Accra has been given the sad name as the most polluted in Africa. Are we safe? Most polluted in Africa, most polluted area in Africa. And certainly this is an undisputable fact. If you look at what is happening in this slide, after before they get the metals, they burn the whole WEE to burn the plastics off, and then you get the metals out. Are we safe? Now, how do we resolve this? How do we resolve this? Several research is currently ongoing in this area. People are doing incineration, like we see in Abu Dhabi and the rest, with the associated production of various carcinogens. Others are doing pyrometallurgical recovery. There are yet researchers who are doing hydrometallurgical processing to get the metals out. In the next moment, I'm going to take you through a bit of the work that we have started at UMaT, namely the simultaneous pyrolysis and pyrometallurgical recovery of liquid fuels, solid fuel like carbon, and then various categories of metals. Now, one thing that is certain about this process is that in addition to copper, which is the major metal in WEE, along with maybe tin, lead, and so on and so forth, precious groups of metals like silver, gold, platinum, and palladium are also present. And let me make this fact that the grade of these precious groups of metals is higher than in naturally occurring ores. So in doing this, this is cheaper way of getting the metals out. And then in terms of doing damage to the environment, it is also safer, even though we see things being done in the crude way to pollute cities and suburbs in Accra. Now, this is a typical composition of waste, electronic and electrical equipment. Like I said, we have refractory oxides that could go up to about 30%, plastics that could go up to about 30%, copper up to about 20%, iron about 8%, tin about 4%, nickel, and so on and so forth. So as you can see from this slide, WEEE or WEEE is a heterogeneous material. it is a heterogeneous material. How do we deal with this material so that we can create jobs, can create values, we can create resources? Now, going further, I have broken this down based on the work done by Eurostat 2015, 2012, 2013. So you see that even as you move on, things become even more complicated and complex. How do you get these materials out? E-waste recyclable. They contain glass, they contain plastic, and as usual, they contain metal, which is typically copper as a main constituent, and then a few other materials. Now, the objectives of my presentation today is to let us discuss about sustainable processing of WEEE. And by sustainable processing, I'm talking about a safe environment and then having human health into consideration. Now, we also want to view WEEE in terms of a resource for secondary metallurgy. So you see it as a raw material rather than as a waste material. And when we do that, we're talking about urban mining, because most of these materials are typically discarded in urban areas. And of course, if you're able to do this, then I am sure we can create jobs out of this environmental pandemonium. Now, target resources. So if I take WEEE and then I want to process it, what exactly am I looking for? Now, the first thing is liquid fuel. And by liquid fuel, for safety purposes, we will always want to restrict ourselves to the diesel range of liquid fuels, namely diesel, kerosene, aviation fuel. Now, we also have solid fuel in them because the material contains both plastics and the wood as well. So certainly when we treat it by high temperature applications, we are certainly going to end up with some solid fuel in the form of char. Now, this char can be used for so many things. You turn it into activated carbon if you do activation. You can also produce metallurgical coke from it by carbonation. Okay. We also have the platinum group of metals like platinum, palladium, and so on and so forth. Precious metals, gold, silver. Palladium is currently more expensive than gold, so I can also place it under precious metals. Then other metals. I mentioned that the major component is copper. Of course, we also have tin, we have lead, and all these are materials that can be salvaged to create jobs for the teeming unemployed youth in the country. Now, a bit about what we've been doing currently. I have my WEEE over there, and as you can see, in addition to that, I have various forms of plastics. I have HDP, I have PS, I have another form of HDP. You can put any other plastic there, PP, LDP, LDP, and so on and so forth. So any form of plastic, you can combine this with the WEEE. Remember, the WEEE also has its own polymers. PP is there, HDP is there, PS is there, ABS is there, SAN, and so on and so forth. So various forms of plastics. In fact, the everyday plastics that we see in the environment, they are all there in the WEEE. Now, this is the scheme. Now, if you look at this scheme critically, it is not very different from the way we produce our diesel from our plastic waste. The idea is that we want to use about the same system to create our resources without making too much modification to the existing facility that we have. Otherwise, additional costs may have to be taken into consideration. So I have attempted to combine my WEEE, especially the printed circuit boards, with PS, polystyrene, with PP, polypropylene, with HDP, high density polyethylene. In fact, you can get most other plastics that you can put them there without causing any disruption to whatever we want to achieve. Now, This is first subjected to a pyrolysis reactor. The idea is that the plastics will require a lower temperature to get whatever I need from them, as opposed to the metals. So my first idea is that I put the whole thing together and begin with my usual pyrolysis process. Now, as a result of a pyrolysis, every gas that will come out of the pyrolysis reactor is condensed first in the condenser A, and then I move it to second condenser B. Now, in the second condenser, I am able to separate out my oil, which I can store, a bit of the flue gases like methane, in fact, from C1 to C4. All the gas within C1 to C4 is usually very difficult to condense. So they may go out, but it's a way that we are trying to do so that we can fetch them back into the reactor to bring about the heat. So we want to maybe use them as a source of fuel by diverting them back to the pyrolysis reactor. Now we get our usual fuel, and then what do we have in the reactor? A system consisting of all the metals that were in the WEE and the PCB. And it works brilliantly, and very surprisingly, it works. So nothing is changed, so to speak. So after taking out my diesel, I can get my metals out, and then I treat them further. Let's move on. This is a basic equipment that we use in our oil production. So I put everything together over here, and I do my usual control pyrolysis. I use the term control pyrolysis, but because here there's a need to make some temperature modification, unlike the normal diesel that we produce. So that was done. And then once I get my fuel out, the metal components that are not able to undergo any melting. In fact, most of the metals at the temperature that we produce the diesel will not undergo any melting, with the exception of lead, some aspect of the lead, and then some aspect of the tin, whose melting points are below the temperature needed to do my pyrolysis. So now, if you look at the picture over here in this slide, if I'm able to take my plastics, my polymers, my everything away, I can then do my normal heating without producing any gases whatsoever. So after I have been able to convert the plastics out of the PCBs, out of the WEEs, I can then do what I would call an environmentally benign pyrometallurgical process, where I can melt all the metals, and after that, I'll do a deportment of the metals. Something strange happens. Let's see what happens. Now, recent results. Now, before I did the work, we were interested in seeing the various forms of WEEs or the PCBs. We first considered that of laptop, and when we did heat the laptop, the PCB from laptops, we realized that the metal fraction was around about 29.5%. The gas was about 43.5%. Then the residue was about 37.0%. Now remember, now this gas, if you look at this slide, you notice that the gaseous component is the major component. Now, so if you go to Agogoshi or whatever, and we have our guys over there doing their crude form of incineration, this 43.5% of gas is going to go out. And because you may have some plastics like PVC and co, you end up producing this PAH, polyaromatic hydrocarbons, and furans and dioxins. Now, these are all potential carcinogens. So when they burn it openly, 43% of the material, which is a gas, will escape, and then it will end up polluting the environment. Let's move on to the PCB from end-of-life mobile phones. As you can see, once again, the gas or the gaseous component is the major component. The metal is now 34.17, and then the residue is 24.17%. You go to PCB from end of life TVs. The gaseous component has now shot up to about 60.5%, metal down to 13.5%, and then the residue based on around 26.0%. Now, with this in mind, selection, we're able to select carefully the proportions that we should combine with the normal polymers so we can do our pyrolysis. Now, these are some of the products, typical products. You are likely to end up with a liquid fuel, and then you also have tar residue. Remember, now this tar residue, this one looks a bit liquid, but it's a solid. Sometimes you may end up in a very solid tar material. As you can see, tar residue, they are very rich in carbon and hydrogen. And carbon and hydrogen are ideal reducing agents. So currently, the plan is that once you get this tar or char, these are ideal reductants for government's proposed integrated iron and steel corporation that was launched in 2018. So in dealing with our PCBs, we get the viable material that we get, but the residue that we get is not waste material. In fact, it is yet ready to begin its work as another feedstock for another process that government launched a few years ago. Yeah, Joel, please, you have a question? Hello, Joel. Okay, let's move on. Now, we get so many forms of fuel, not different from the fuel that we get from our normal pyrolysis of waste plastics. Various forms. Aviation fuel, diesel, kerosene, we get all of them when we combine this with the normal waste plastics to produce our fuel. Now, there is excellent deportment of metals into different phases when we do the pyrometallurgical, the controlled pyrometallurgical process. Now, the various phases, normally we have about 3 phases: the gaseous phase, the metals phase, and then the metals phase, we have what we call the copper-rich phase, and then the copper deficient phase. Now, by the copper deficient phase, typically in the absence of copper, you just have tin and lead. And you see, because tin and lead have very low melting points, they are able to undergo melting easily, and then they are able to take up part of the metals within the system. So for here, I will just group this into a 2 metals phase, a copper-rich phase, and then a copper deficient phase. And by copper deficient phase, I mean my tin lead phase. Now, look at the copper-rich phase. You will notice that predominantly the metals will consist of copper. But as you move on, you will notice that even though we have several spheres right here, we may have some of them that may contain other metals like gold, palladium, and so on and so forth. Now, this is the metals, various metals that we get in the copper deficient phase or the tin lead phase. I don't know whether the color is saying something, but you see, look at the copper rich phase and then look at the copper deficient phase. Of course, if you look at the color of lead and then tin, you shouldn't be surprised why the copper deficient phase looks like what you see over there. Now, a bit about the recovered metals. Our preliminary results indicate that we can get silver, the grade up to 1,400 ppm in the copper deficient or tin lead phase, usually temperatures between 800 and 1,000 degrees Celsius. Now look at the gold, 7,000 ppm. In fact, we are able to exceed about 7,000 ppm in the copper rich phase. I want to believe that currently we know the various mining companies. the gold that they are able to extract from their ores. We also we have an idea about, especially the minerals engineers, the metallurgists, the mining engineers, and so on. The grade at which they go for the ore. Gold can go up to 7,000 ppm in the copper rich phase. And this is just temperatures within 800 and 1,000 degrees Celsius. Platinum, more than 20 ppm, also in the copper deficient phase. Palladium, more than 300 ppm in the copper rich phase. So you see that the PCBs, the WEEs, when we are throwing them away, when we are burning them, and then we are causing producing a lot of dangerous gases, carcinogenic gases that cause people to become sick, then we are doing ourselves more harm than good. It is an indisputable fact that this waste stream is a rich source of raw materials for urban mining. We did a bit of GC mass analysis of some of the fuels that we produce. Please forgive me about that one. We want to move to a stage where, like I said, we use a normal diesel production plant from waste classes to do the work by slight modifications without introducing anything, any major modifications, so that we can save costs. So this is a typical commercial plant that we want to build. This is based on the work by Besting and Co. In doing this, we have the Besting technology mind. We'll build something similar to that. And the idea is that land is expensive in Ghana. So what we want to do is we want to come up with a technology that can conserve land so that we'll create the jobs that we need to create. Now, conclusion. These days, there's nothing like waste. Every waste material is a potential resource. Every waste material is a potential resource. If you buy pure water sachet and then you drop down the water, you take the contents of the sachet by taking the water out. The sachet that is left is not a waste material. At best, it is an end-of-life material. It will have serving its purpose as a waste, its purpose as carrying the water that you drank. But after you have taken the water out, it is ready for yet another function or another task. So it is not a waste material. The next thing, our WEE, our PCBs and the like can be handled in an environmentally benign way to create jobs. If you throw them away, we are just throwing resources away, and something that could otherwise have been used to create jobs, we leave it to the more broad people to work to eke a living and then to pollute the environment for us. And then finally, a lot of resources went into doing this work. We heard about the National Research Council some years ago. I think, if I can remember, about 6 years ago. Nothing has been done about it. There are a lot of things that can be done, and I pray that one day the National Research Council will come on board for us to get some funding to be able to do our work. Thank you very much, and God bless us for our thoughts for answers. I didn't have to go on. Okay. Mr. President, I'm done.
Yes, Prof. I think there's this question from NS Yankee. He says, he's asking who will provide the funds to start this project. And when do you
he's asking who is going to provide the fund?
Yes, and when do you start it?
Typical of our part of the world, every research that we do mostly is self-funding. I take a look at our miserable salaries, and then out of this, we usually do so many kinds of work and the like. Uh, this the usual mantra: you perish, you publish, or you perish. We don't want to perish, so we'll publish, and then we'll do our research. I hope that government will come
in case we can get some investors.
Oh yes, we can. We did something small some time ago. If we get about because I'm going to combine it with the diesel production process. Anything around about anything around $1 million should be able to set up a very big one to create jobs. But remember, the cost can go down. But to be able to set up something so that we can come out with the jobs that we need to create, $1 million should be able to do the trade, and then we get the jobs that we want to. Otherwise, from the point of view of research alone, I think anything, even about a third or even a tenth of that can do. We can do something, start something from there.
Can a typical pyrolysis plant be used for extracting precious metals from discarded electronics?
This is a simultaneous pyrolysis controlled pyrometallurgical application. A simultaneous pyrolysis combined with a controlled pyrometallurgical process. The PCB or the WEEE could contain up to about 30% plastics. And it is this fraction, the plastic component, that will normally do the damage to our environment, the damage to the inhabitants, those who are not involved in the WEEE processing, they are also affected in some way. Because when you have the gases moving out, it's not only polluting those who are involved, but those who are not involved will also be polluted. So it's not just about just a pyrolysis plant alone, but a combination pyrolysis plant coupled with a pyrometallurgical plant can do the job. I don't know whether the question is answered.
I should think so, but then this is from William Forson.
Yeah.
Just to generate 1 liter of liquid fuel, how many end-of-life laptops do you have to work with?
I mentioned that when I take a mobile phone, the object or the major material that I look for in the mobile phone is the metal, especially the precious group of metals: gold, palladium, silver. So, but the mobile phone also contains up to about 30% plastics. So when I take a mobile phone, what I need in the mobile phone is not the fuel itself, but it is the metal that is there. Of course, I don't want to pollute the environment. And I know that because the polymer there is about 30%, if I'm to go by heating, the 30% polymer will escape and it will cause problems. So when I take the mobile phone, it is only the 30% of the mobile phone that can give me the fuel that I want. But this is an integrated process. So I combine it with my normal waste plastics. And then all that is happening is that the polymer from the mobile phone will move and join the normal pyrolysis process so that I can get my fuel. So I would rather not measure the yield of the fuel in terms of liters from the point of view of the mobile phone, but rather from the point of view of the plastics that I'm using. Now, if I were to go by the plastics, then every liter of plastics that are pyrolyzed, we started from about every kilogram of plastics that are pyrolyzed. We started from 2014. We were then hovering around about 0.4 liters. Currently, as we speak, we have been able to move beyond 1 liter per kilogram. I'm sure some people may be asking me, how is that possible? But remember, the density of the plastics is lower than that of water. So certainly, I can take 1 kilogram of plastics and then get more than 1 liter. The last time we did the measurement, I think there was one that I got 1.02. There was another one I got 1.1 liters per kilogram. Now, if you translate this to tons, metric tons, then it means that for every metric ton, I'm talking about the plastic component, whether it is from the mobile phone, from the TV, from the laptop, or coupled with the normal waste that I want to create. So if I'm having about a ton of plastic waste, I am able to get 1,000 liters of fuel. 1,000 liters of fuel. Thank you, President.
This is a contribution from Bashir Ahmed.
Okay.
He thinks financing could be attained if a business plan is drawn. If the plan shows a good return, we may not need government intervention to achieve reality. Can we look at the business plan? I mean,
I can provide that. We can work on that. Yeah, this is the latest research that I'm currently doing. And I know that if you take a look at the palladium alone, the gold alone, and then they're like, this is something that can generate a lot of. So certainly we can work out on a business plan, and then if government doesn't need to come in, that is okay. It's fine. I'm okay with that.
Yeah, Prof. Kopimoro is looking at the sustainability position of it in terms of the waste to feed the plant. Do we have enough of that?
I have tried as much as possible to make the process as flexible as possible. The process combines both pyrometallurgical and then pyrolysis process. So you see that it's like trying to kill two birds with one stone. I have made it in such a way that it doesn't depend only on WEE, and it doesn't depend only on the waste process either. So this is something that I'm putting two things together. And when I say polymers, I am not only referring to the normal plastic that you see. These days, this year, for example, we started producing diesel from even end-of-life vehicle tires. End-of-life vehicle tires. The various grease, lubricants that mining companies produce want to decide, and they're like, they are all polymers that can be used in producing the diesel. So in terms of raw materials, I think we have enough. Since the process is flexible and then it can be geared towards either side depending on availability of raw materials. So yes, it is sustainable.
And Darlington Yawson will want you to throw more light on what happens to the fuel gases after the pyrolysis.
Going from the current results that we have tried as much as possible to make the system airtight. So it is as airtight or gas tight as possible. Usually when you have leakages, then you may tend to lose a lot of gases into the environment. Now, we have been able to program the whole thing in such a way that the only point where we have the gas leaving is when after I've taken all the fuel. Now, the last results that we did, out of 1 kilogram, we were able to get about 1.02, and then one was 1.1 liter. Now, if you go by the fact that diesel has a density that typically will range from about it's averaging about 0.82 liters per kilogram. That means that for the 1 kilogram that I use, about 820 grams, okay, will go into the production of the diesel. The other part is the waste material, the solid material, the char or the tar. The gas component so far, we've been able to minimize it to, I think, the last time we checked, it was less than about 1%. Like I said, this gas consists predominantly of carbon chain C1 to C4. So it moves from methane to whatever. And it is combustible. What we want to do is that because we have tubes that can connect this back to the system, we want to have a system where we have a complete system, a closed system where the gas, between 1 to about 4% gas that will come out, we'll channel it back to the reactor so that it can assist in the heating process.
Hey, Prof, thanks, but then...
Is the question answered, please?
Yes, I think so, Prof. It's fine. But then there's this question from Ken Glover. Very interesting question. He saw that aviation fuels, kerosene and the likes were all extracted from the fuel. Was this done by fractional distillation? And if so, will the process be efficient in order to produce commercially pure automobile fuel that could be accepted on the market?
Yes.
See.
What we are beginning to notice, is that the proportion, in fact, when you produce the fuel, almost always you may have a small fraction of petrol that could be part. All right. Currently, we haven't started dealing with the fractional distillation. But if you were to take a look at the slides that I showed, and if you look at the quality of the fuel, the type of fuel that you produce typically depend on the major polymer that you have in the system. As much as possible, because of safety issues, we have tried to avoid producing petrol, because I don't want to store petrol anywhere for now as I begin with this way. So as to whether you are producing kerosene, diesel, or aviation fuel, it will depend on the plastics that you use. For now, I know the plastics we take to produce aviation fuel. I know the plastics we take to produce diesel, and I know the plastics we take to produce kerosene. We have done all this, and then based on some measurements that we did, we take the samples and then we go, we check, we do a GC analysis, we do FTIR analysis, we check the, the other parameters, flash point, pour point, and then light. And then we're able to know that anytime one plastics, a particular type of plastic would dominate, you're either producing either diesel, aviation fuel, or kerosene. So we know when. So for example, if I want to produce predominantly diesel, there are some plastics that I will attempt to minimize its content, and then others I make that is the predominant content. Like I said, this is a flexible process that we can always manage to get what we want. So yes, you can do fractional distillation if you want, especially when you have about 4% petrol being part of the diesel range of fuel. But we also know the places to go. If I want petrol, I know what I can take and I'll produce from petrol. If I want diesel, I know the places I need to go for to produce my diesel. Aviation for the same way. So we still have how to minimize the greater part and then of the unwanted material and then to produce what we want. But diesel, kerosene, and aviation fuel, their properties, they don't vary too much. The only thing that you see from the GC, if you do a GC analysis, it's only the carbon numbers that will change. In terms of density and then they are very close. And yeah, so it's only the carbon numbers. As you move higher, you move from your aviation fuel to diesel to kerosene, depending on the carbon numbers. So it doesn't really vary too much.
Yeah, but then, as a difference, if we are looking at that tedious segregation of plastics,
yeah,
I'm just afraid. I'm looking at the tons of or the volumes of plastics we will need. I mean, for the various processes, is our market able to sustain that?
We have a lot of plastics in the system. We have a lot of polymers in the system. If you use, for example, vehicle tires, you can use it to produce your diesel as well.
Okay.
Of course, then you need to think about the sulfur that is there. one good thing about the polymer, for example, if I take HDP, PP, and so on and so forth, is that these are polymers that typically do not contain sulfur. So I can produce a fuel that I can term as a sulfur-free fuel. But there are other raw materials there. Of course, when we get to a point that we have been able to commercialize, as we speak, in 2017, December 2017, China said no to plastics importation.
Yeah.
So as we speak now, the EU and all other countries are struggling as to how to discard their plastics. Mm-hmm. If we get to a point where we think that we do not have enough plastics and that, we can let them bring it and they pay us to take delivery of their plastics. We don't pay them, we don't buy because they are struggling to dispose of their plastics. So we can still let them, you bring it, we'll charge you, and then we use it to produce our fuel. So that is also possible. And let's not forget about the sub-region as well. Let's not forget about the sub-region. So for now, this is something that is suited to Ghana. But when there's a point where we think that we need more, I think it shouldn't be too much of an issue to get the plastics waste. Because I know some countries are struggling, including the so-called industrialized countries. They are struggling to dispose of their plastics. So to sum it up, we can charge them, take their plastics, and then use it to produce our fuel.
Yeah, Prof, we thank you very much for such a wonderful insight and technological innovation. Thanks so much.
Thank you very much. It's a great pleasure to have had a discussion to share my ideas and then to let people know that certain things can be done in Ghana. Thank you very much.
Hold on, before you go, there's this person that just came in from Dorothy Dechi. Yeah. Said, please, in as much as we would like to get waste out of the system, I think the process will cause a number of carbon emissions. And as there is a global concern on reducing global warming or carbon emissions, has this been considered?
I beg to differ. You talk about carbon emissions, your carbon footprint, when you are getting this carbon into the environment. This is a process that is typically going to divert all these plastics from landfill sites.
Yeah.
Okay. This process is rather diverting all the plastics from landfill sites and then also from potentially from the oceans.
Yes.
If you don't manage the plastics, they will get into the ocean. And already, if you look at the UN statistics that they provided, by 2050, and I think even now it's probably earlier than that, by 2050, we're going to have more plastics in the oceans than we have fish. Yeah. So certainly when we're talking about carbon footprint, this is a technology that is taking all the carbon away, and it is giving you diesel range of fuel. You're getting your metals out of them. The 4%, they're about 1 to 2, 3, 4% of the C1, C4. We are diverting back into the system. The carbon emissions are not very different from those that we get from burning normal wood or normal fuel for this process. In fact, they are lower. So this is a process that is rather going to decrease the carbon footprint rather than increase the carbon footprint.
Yeah, I agree with you. I agree very much with you. Prof, thanks so much. We're grateful as always.
Thank you.
Yeah, this webinar will be posted on the WAIMM YouTube for everybody to refer. Prof will also be around with your questions. We will forward the questions to him to respond to them appropriately. Thanks for making time with us, everyone. And let's meet again same time next week for another insightful and innovative webinar as part of the WAIMM webinar series. Thank you very much.